Welcome everybody. In the next 30 minutes or so, I will try to tell you as much as possible about FLAVIN-dependent halogenases. And I will go through some history, some background information, but I also want to show you some of the latest papers in biocatalysis. So let's dig right into some background informations. So when we think about halogenation, some names pop up in our head like electrophilic aromatic substitution, radical substitution, or electrophilic addition. And when we look at the electrophilic aromatic substitution, usually we know that this involves the reaction at the most activated sites. So for example, for phenols or aniline, we have several activated sites like the ortho and para position. And of course, this leads to a mixture of products, and this lack of selectivity between electronically activated sites limits the overall yield and efficiency of the reaction. In this work from 2014, the authors use aluminum affinity calculations to quantify the nucleophility of different sites on a molecule. And their point was that, of course, when you have a site like this one, this C2, that is the most activated site, you cannot access the halogenation of these other sites that are less electronically activated via standard electrophilic aromatic substitution strategies. Halogenation, on the other hand, in nature occurs with enzymes that are called halogenases, and were found also both in marine. Also, halogenases were found in terrestrial organisms. The biosynthesis of halogenated compound, also called organohalogens, in these organisms serve a range of biological function like growth, reproduction, and defense. Here I reported two examples, like this terpene here, produced by algae, and also this simple bromobenzene that is usually detected in oak moss. We also know that organohalogens play a very important role in the pharmaceutical industry, and many biological and medical functions were attributed to halogenated compounds. Halogenases were found more or less in the last 50 years, and usually when we try to group them, we divide them in according to the mechanism they use for the installation of the halogen atom, and therefore we have electrophilic mechanism, which includes heme-dependent, vanadium-dependent, and FLAVIN-dependent halogenases, but also nucleophilic with some fluorinases, and radical with non-heme iron ketoglutarate dependent halogenases. But as you probably guessed, today we will just focus on FLAVIN dependent halogenases. So in a nutshell, what these FLAVIN dependent halogenases can do is the installation of an halogen atom to a substrate using reduced FLAVIN, oxygen, and a source of halide. Now let's have a little look about some historical artifacts. So FLAVIN-dependent halogenases are actually quite young. So the first report is from from 1998, and here the group of researchers was actually looking for the biosynthetic pathway that lead to this antifungal agent here, and they came across this enzyme called PRNA in the organism Pseudomonas fluorescens. And this enzyme was held responsible for the halogenation at the 7th position of the indole moiety of L-tryptophan. Following this discovery, many more L-tryptophan FDHs, which is the short for flavin-dependent halogenases, were discovered and described, and also they were described to have different regioselectivity than the one that I just described to you. So they were not only able to perform at the 7th position, but also at the 6th or at the 5th position. Just to give you some names that we will find throughout the presentation, we will see many times this RebH, which is regioselective for the 7th position, but also TAL and PAR-H, which can halogenate at different position. But now the question is actually, is this class of enzyme only bound for the halogenation of L-tryptophan, or we have a wider substrate scope? And this question brings us straight next to this section that is involving the enzymatic diversity and the substrate scope. Actually, after a while, it was clear that these enzymes were not just performing halogenation on L-tryptophan, and especially in the mid-2000s, when this class here marked in yellow was discovered, this was even more true. In fact, these enzymes here were having a very high sequence identity with already known tryptophan FDHs, but they were not converting tryptophan. Instead, they were halogenating smaller molecules like indoles. Following this discovery, many more FDHs with a different substrate spectrum were described, and a new subdivision arose according to substrate preference. So now we can talk about tryptophan FDHs, indole, phenolic, and pyrrolic. So just to have an idea on how broad the substrate scope can be, some of these enzymes still convert quite small molecules like this one here, like this PLTM, but recent reports also found enzymes that can operate on bulkier substrate like this one. Stressing again on the remarkable diversity of this class of enzyme, here are some examples of native and non-native substrate that can be halogenated by FDHs. And I want to mention briefly these two enzymes here that were reported to actually be involved in the biosynthesis of these two compounds. So therefore, they were held responsible for the halogenation at an aliphatic site. Even though the exact substrate is not identified yet, is still very remarkable. Even though till now I was just showing you chlorination examples, FDHs have been shown to introduce all common halides except for the very electronegative fluoride ion. Nevertheless, a certain anion preference still exists. So the well-described tryptophan FDHs like RebH, TAL, or PAR-H still prefer chlorination over bromination, where basically all the others can listed here can actually perform both. On the other hand, when we talk about indole FDHs, this preference is actually the opposite, so bromination over chlorination usually. And also we can note here that some FDHs were found to be also able to perform iodination. Let's now dig in some structural features, and also let's look a little bit close to the mechanism of these enzymes. So most of our understanding on FDHs comes from the study of tryptophan FDHs like PRNA, if you remember, is the first example of this class of enzymes. And what I want you to focus now is this FAD binding site. because when you compare different tryptophan FDHs, you can see that this domain is quite conserved. So meaning that this domain is essential for catalysis. On the other hand, the C-terminus is quite diverse, so this region is thought to impart the substrate specificity for different FDHs. So FDHs are not just resembling among themselves, but they are also very looking alike FLAVIN-dependent oxygenases, both mechanistically and structurally. We know that both class of enzymes use reduced FAD that upon reaction with oxygen leads to the formation of this reactive species here. So in FLAVIN-dependent oxygenases, what happens is that the substrate is quite close to this intermediate here, so the oxidation is going directly onto the substrate. When we look at the same picture for FLAVIN-dependent halogenases, we can see that the substrate is way too far away to be directly oxidized. So what is supposed to happen is that instead the oxidation of an halide is taking place. But let's look a little bit closer to this mechanism. So we just saw that on the FLAVIN binding site, this reactive species is reacting with a chlorine ion, and therefore hypochlorous acid is formed. This species is believed to travel through a tunnel of around 10 angstrom, and therefore arriving on the other substrate binding site, and is supposed to react with a lysine residue. It's still not clear if there is only some hydrogen bonding going on, or if a chloramine intermediate is forming. Nevertheless, in this step, the reaction, the chlorination is actually taking place, and therefore the product is formed. There are no doubt that this lysine residue here is responsible and necessary for the catalysis. In fact, upon any mutation of this residue, there is no activity at all. Actually, this residue is also very important for regioselectivity, as we can see in this slide. Upon the different positioning within the active site, the CH bond that is most close to this lysine here is then the one that is going to be functionalized. So in this case, we can also see that there is another residue that is highlighted here, and is a glutamate residue. And this glutamate residue lately is also held responsible for part of the catalysis somehow. In fact, upon mutation, also the rate of the halogenation is slowing down, is dropping actually. So what is glutamate residue believed to do? Probably is deprotonating the valent intermediate that is formed upon halogenation. But also no kinetic isotope effect was observed. Therefore, this is not the rate limiting step, where probably this glutamate residue is assisting also the positive charge formation, and the valent intermediate formation is actually the rate limiting step. So now that we know all this information about how the installation of the halogen atom is going on, then let's look at some biocatalysis informations. As we can deduce from the reaction mechanism that we just saw, the catalytic halogenation, the biocatalytic halogenation relies upon constant supply of FLAVIN-dependent halogenases. Reduced FLAVIN. In In nature, the oxidized flavin species is produced by a flavin reductase, in short FLAVIN, and in case of halogenases like RebH, for example, the corresponding flavin dependent the flavin reductase was found in the same native organisms. Likewise, for the flavin dependent halogenase found in Pseudomonas fluorescens. But these flavin reductase, they rely upon also constant supply of NDH, so therefore for biocatalytic purposes we need another additional enzyme, so this could be a GDH or an ADH for the recycling of NDH. So despite the very unique site-selective halogenation performed by flavin-dependent halogenases, of course the introduction of a cofactor recycling system renders the biocatalytic reaction more complicated and also harder to scale up. Consequently, several studies address the drawbacks of this cofactor regeneration system. First example that I want to show you was published in 2017, where a fusion construct was built for linking together RebH and its flavin reductase RebF. And also they showed that basically with this fusion construct they could have higher product titers in vivo, both for native and non-native substrate compared to the co-expression of the individual proteins. An alternative strategy proposed in 2015 was initially expressing this protein individually, and afterwards they were cross-linking them together with the so-called conbiclease aggregates. And with this, they showed that they could perform the biocatalytic halogenation with basically perfect conversions, but moreover, they could demonstrate that they could reuse this conbiclease up to 10 times without any loss of activity. Another example comes from 2018, where remarkably these authors were just employing light, a sacrificial electron donor like a DTA, for the recycling of FAD. They also comment that for sure there was a lower turnover frequency compared to the enzymatic regeneration system, but nevertheless I found this work very interesting anyway. Another example from last year was employing NDH mimics for the regeneration of reduced flavin. And here they also employed different FDHs for the functionalization at different positions of the indole moiety. So despite FDHs are powerful biocatalysts because of their unique active sites, there are still some drawbacks, especially FDHs are typically suffering from relatively low kinetic efficiency, and also several studies reported total turnover numbers of less than 200. So basically a lot of protein engineering was employed for addressing these drawbacks. But also for enlarging the substrate scope and improving the thermal stability. So I divided the protein engineering work that I found between thermal stability and activity, and also for the substrate scope. So when we look at this first group of works, here are just listed some, but there are many, many more in literature, and also today I will just mention one. So in this work from 2014, they performed 3 rounds of error-prone PCR and recombination, and they could obtain a variant here that was 18 degrees increased in the melting temperature compared to the wild type. However, catalytic efficiency of the mutant was significantly decreased at 21 degrees, as we can see here. But of course, the authors comment that this outcome is consistent with the notion that when you have a decreased conformational flexibility, then this can be beneficial for stability, of course, but it can be detrimental for activity. When they were looking at some of the mutations that were performed to obtain this variant, they were commenting especially on this mutation here around this area that is on the surface of the protein and is between 2 arginine residues. And what they comment is that when you look at the wild type with the lysine residue, you have a higher positive density around this residue here, around the lysine, and therefore when you substitute with a methionine, you might yield stability by reducing the charge density at this position. Also, what they comment is that the side chain of the methionine has a conformation that enhances packing with neighboring residue, and this might also yield to more thermostability. As I already anticipated, the other part about protein engineering was dealing with substrate scope and regioselectivity. And also here the literature is very, it's going beyond the one listed here, but I also will show you one example for this. So in this work, they were dealing with the biosynthesis of monoterpene indole alkaloids, which commence with the decarboxylation of tryptophan upon the use of tryptophan decarboxylase, and therefore this tryptamine 2 is generated, which with cyclohexane are the precursor of the monoterpene indole alkaloid here 4. It's already known in literature that you can install the FLAVIN-dependent halogenase in this biosynthetic pathway to generate these chlorinated analogs 4B. The problem here is that the tryptophan decarboxylase has a preference 30-fold for 1 instead of 1B. Therefore, what is happening in vivo is that 1B is very much accumulated, and therefore the formation of 4B is somehow hampered. Therefore, what they wanted to achieve with this work was to re-engineer the RebH to perform the halogenation preferentially on 2 and then avoid accumulation of 1B. Of course, after 17 mutations, which were mostly here in this area, so where the residues that were mostly interacting with the carboxylate moiety of tryptophan, they could find a mutant that is reported here that was preferentially accepting tryptamine instead of tryptophan and was still actually halogenating at the 7th position. I also wanted to mention some of the CHEMOENZYMATIC work that I found out in literature. Also here, the same argument applies, that there are many more examples than the one listed here. I just didn't have enough space. And also in this case, I will just show you one example. So in this work from 2016, what they were doing was to link a biocatalytic halogenation, which they performed using the combi-class aggregates strategy to achieve this halogenated tryptophan here, and they were also using different tryptophan halogenases to perform the halogenation at different sites of the indole moiety. And also what they comment is that they didn't have to perform any isolation because the reaction is very selective and quantitative, and moreover the combi class aggregates could just be filtered out. What they were doing was to link this biocatalytic halogenation with a cross-coupling, Suzuki cross-coupling, and they could do this just by adding two palladium catalysts, a boronic acid, and a base, and therefore they could obtain 3 in just one pot reaction without any isolation step in between as well. At this point, they could just isolate 3. Or what they could do was to just perform a final step, bulk protection, and therefore achieve this compound 4 here that is used directly for further peptide synthesis. So I hope that with this short presentation we could uncover a little bit the tip of the iceberg for this topic. And there is going to be an email that you could use for any question you will have about this topic. And with this, I would like to close this presentation saying thank you for participating and listening.